Hey everyone, today we are getting into something that, honestly, every single applied QCA researcher needs to know about. It's a powerful protocol from Oana and Schneider, and it's going to help us move from just doing random ad hoc checks to having a systematic, totally defensible way to test our results. Let's jump right in. So, you know the feeling, right? You've spent weeks, maybe even months on your QCA. You've nailed down your calibration, you've built your truth table, and you finally have a solution that just clicks. It makes perfect theoretical sense. But then, that little voice in the back of your head starts nagging you. What if I just nudge that calibration anchor a little bit, or change the consistency threshold by 0.01? Would my whole finding just vanish? Well, that's exactly the fear we're going to tackle today. So here's our game plan. We're going to start with your main model, what the protocol calls the initial solution. Then we'll hit the first, most basic check, sensitivity ranges. After that, we'll dive into the really cool stuff, the core concepts of the robust core and test sets. From there, it's all about practical application, a step-by-step guide to the full protocol, and finally, how to read the results and deliver a clear verdict on your findings. Okay, let's get into it. First things first, we need a starting point, right? This whole protocol is built around testing the stability of your number one main finding. And that brings us to the initial solution, or IS for short. Now, this isn't just some random output. This is your baby. It's the solution you've meticulously built, backing it up with all your deep theoretical and case knowledge. This is the finding you're ready to stand by. And really, it's the hero of our story today. Everything we do from this point forward is designed to see just how well our hero holds up when things get tough. And why do we have to put it through the ringer? Well, because QCA, as we all know, involves a ton of judgment calls. Where you set your calibration anchors, what consistency thresholds you decide on, your frequency cutoff, these are all spots where another perfectly reasonable researcher could make a slightly different choice. The goal here isn't to pretend there's one single true model. It's to prove that your conclusions are solid, and not just some fragile accident of one very specific combination of choices. So the protocol starts us off with the simplest, most intuitive test. It basically asks, how much wiggle room do you have on any single one of your parameters before your solution formula actually changes? Okay, now this slide is super important because it draws a really crucial line in the sand. On one side, you have the sensitivity range. Think of this as what the data is telling you. It's the safe zone. You can tweak a single calibration anchor within this range and nothing happens. Your solution stays the same. But then you've got the hard test range. This is based on your theory and your expertise. It's the range of values that are still conceptually defensible, even if they fall outside that empirically safe zone. And this is the key takeaway. The best robustness tests are these hard tests that really push your model to its plausible limits. And this image just lays it all out perfectly. Look at scenario 1. That's great. Your theoretically plausible range is totally inside that stable zone. But the real test of your finding strength, that's scenarios 2 and 3. That's where you intentionally push your parameters into that hard test range just to see what happens. A finding that can survive that kind of pressure, now that's something you can really be confident in. So, checking one parameter at a time is useful, for sure. But the real world is messy. What happens when you change multiple things all at once? To answer that, we need to get our heads around the two core concepts of this protocol: test sets and the robust core. Okay, take a look at this diagram. This is basically the conceptual heart of the whole protocol. On the right, you've got your initial solution, your IS. On the left, you have your test sets. Now, that's just a fancy term for all the alternative solutions you create by making all those plausible changes. The min TS is what all those alternatives agree on. The max TS is basically everything they could possibly produce. But that shaded area in the middle, that overlap, that's the prize. That is your robust core. So let's nail this down. The robust core, or RC, is the part of your finding that is absolutely unshakable. It's the piece of your initial solution that stays true no matter which of your alternative, totally plausible models you throw at it. This is the answer to that nagging doubt we all have. This is the part of your argument that is standing on solid rock. And what's great is that this protocol also brings us back to what makes QCA so powerful, the individual cases. This diagram helps us sort them out. Any case that's in your initial solution and in the robust core is what we'd call robust typical. But what about the cases that were in your solution but then disappear when you run the tests? Those are shaky. And what about new cases that suddenly appear in the alternative solutions? Those are possible. This tells you not just if your solution is robust, but how it's robust and for which cases. I mean, that's pure gold for your results section. All right, we've got the concepts down. Now let's get practical. How do you actually turn all this into an actionable workflow for your own research project? So the protocol gives us 4 key numbers to look at, called robustness fit parameters. They're all on a simple 0 to 1 scale, where 1 means perfect robustness. RF cons and RF cov are pretty straightforward. They compare your robust core to your original solution. They're basically asking, okay, after all these tough tests, how much of my original story's explanatory power did I actually lose? The other two, RFSC min TS and RFSC max TS, they measure the overall family resemblance between your solution and all those other alternative models you generated. And here is the best part for those of us who are actually doing the analysis. You don't have to do this by hand. The SetMethods package in R automates the whole thing, and the workflow makes perfect sense. But you've got to run them in this order. First, you use rob.calibrange to explore your sensitivity. Second, you generate your alternatives and bundle them into your test set. Then you just run rob.fit for the parameters, rob.cases to see what's up with your cases, and finally, rob.exploit to see it all beautifully visualized. Okay, you've run the code, you have the numbers. Now for the most important part, interpretation. What does this all actually mean for your research? This XY plot, this is going to be your best friend. It is your single best diagnostic tool. It plots every case based on its membership in your initial solution on the x-axis against its membership in the test sets on the y-axis. The cases you can feel really, really good about are all clustered in that upper right quadrant. Those are your robust cases. They're in your model and they stay there no matter what you throw at them. Now, the quadrants you really need to zoom in on are the ones off that main diagonal. Down in the lower right, those are your shaky cases. They looked good in your first model, but they just don't survive the stress tests. You have to be really careful when you talk about them. And then up in the upper left, those are your possible cases. Your model didn't explain them, but other plausible models do. I mean, that's a fantastic signpost pointing right to where your future research should go. So let's make this super concrete for your own project. When you get these results, here's what you do. Pick a specific case from your data. Ask, is this case in my initial solution? Yes. Okay. Is it also in the robust core? Yes again. Great. You can now talk about that case with a very high degree of confidence. But if it's in your IS but it is not in the RC, that's a red flag. It means you have to add a caveat. You have to describe that case as being only weakly or shakily explained by your model. And there you have it. This is your final checklist for totally bulletproofing your QCA results. It's a clear 7-step process that takes you all the way from defining your best model to making a nuanced, highly defensible judgment about its stability. See, this isn't just about getting one little number at the end. It's about deeply, truly understanding your causal claims and knowing the exact status of every single case in your analysis. Look, this protocol really is a game changer. It takes robustness out of the footnotes and puts it right at the center of your analytical story where it belongs. It gives you both the concepts and the practical tools to put your findings to the test. So really, the only question left is which one of your own research findings are you ready to put under the microscope first? Thanks for tuning in.